Okay, I'll let Mr. Murphy introduce himself properly, but we've got Dave Murphy in to give a talk on Flat Earth 101, but first some words from Mr. Bantoa.
Welcome. I just wanted to say before we all begin, it's great to see so many of you here. Obviously, a very healthy atmosphere in here already. Please do maintain decorum throughout the talk, and remember that you are representing UCS, and although that the speaker's views may differ from yours, that is not justification for you to be disrespectful in any way. Thank you.
All right, thank you. And without further ado, Mr. Dave Murphy.
Hello, everyone.
Hello.
My name's Dave. I'm also known as Allegedly Dave. I've been looking at the flat Earth since the summer of 2014. It was a new thing on me. I was like, you know, I guess like most of you, the idea of flat Earth, you know, crazy. But this video I started watching basically said something that piqued my interest. And I've got a lot, there's a lot of this subject, a whole lot on this subject. So what I'm going to do is I'm going to concentrate on one aspect of the flat Earth, and it's going to cover a few other little aspects of the flat Earth as well. So I'm covering the search for the curvature, okay? So this is Neil deGrasse Tyson.
If you send a ship straight to the horizon, eventually it begins to disappear until it's no longer visible beyond your horizon.
Right.
And you should ask yourself, what kind of surface would produce that result?
So that was Neil deGrasse Tyson. He's a leading physicist in America. Okay, and what he was explaining there was I guess the first so-called proof of the globe Earth, that you can stand on a beach and watch a ship go out to sea, and it will appear like the hull sink down below the horizon first, and then the mast. Everyone got that? Yeah. Audience participation? Yeah. Okay. So, one word. The Nikon Coolpix P900. This is the flat Earth camera of choice. It's got an amazing zoom, 83 times zoom. In fact, the new camera, the P1000, is made of liquid metal. The P1000 has got a 125 times zoom, which is just amazing. Right? So this is the camera that dispels that whole myth. And as you can see here, well, you can barely see, there's nothing on the horizon. We're going to watch it zoom in.
Do you think you can see people on it?
They're walking about.
Man, that is a long way away. And that is a long way down.
So basically this was on the horizon, it was gone, it was out of human vision, supposedly over the curve, but the zoom brought it back again. So what we found is that when you get at sort of high levels of zoom, what happens is there's a band of reflection. It's called Fata Morgana. Okay, it's a band of reflection that obscures the real horizon and gives you a false horizon. So this is a false horizon, and this band here is literally just reflecting what's ever above it, and the real horizon is being hidden by that band. Now you might have seen this before on a hot day when a car is coming towards you on the road and you see that heat haze and it looks like the car's going through water. Anyone seen that? Yeah? That's the same effect. But this is what makes it look like the object is going down behind the horizon. So you can see here, this is a tanker, and you can see that line here, and you can see the bridge of the tanker being reflected back. Can you just about see that? Yeah. So, and this horizon is the false horizon. The actual horizon is somewhere, you know, hidden behind that band. So literally, we've got balloon footage up to 121,000 feet high, and it's perfectly flat. Whenever you see you know, these balloons that go up and you see the curve, it's because it's got a fisheye lens, a wide-angle lens. And literally, if you see any of these videos of, you know, where you get the curve, and the balloon is sort of moving up and down, you'll notice that the curve, as the balloon goes down, the curve gets bigger. If the balloon goes up, right, the curve goes the other way. So it's telling you that it's a fisheye lens. This place is a place in Siberia. It's called Lake Baikal. It's 194 miles long, okay, and every winter it freezes over, okay. So it freezes over, and it's perfectly flat, even though it should have a curve in it over 195 miles, about 5 miles of a curve, okay. But the point is, the reflection on that lake is perfectly flat, and we can tell if a reflection is even slightly, you know, marred, then you get a weird reflection. You don't get that unlike Lake Baikal. So to ask Neil deGrasse Tyson's same question, what sort of surface would we see these effects on? You know, here we see reality. So when the sun goes down over water, the kind of reflection of the sun's light literally goes all the way down to your feet. That's only possible on a flat surface. Because if you think on a curved surface, the light is actually behind the curve, and you might see some on the horizon, but it won't come to you. And this is again the P900. It is going to zoom in on this sunset. Okay, most of us have seen the sunset, you know, on the ocean. So the ocean kind of cuts off half the sun, yeah, as it goes down. Well, this is what's really happening. Zoom in on it a second. So it's not gone down behind the curve, it's just an optical illusion. It's literally an optical illusion. Now if you imagine yourself in a long corridor, and there are lights on the ceiling, yeah? If you look down that corridor, perspective means that you'll see everything, you know, to left and right of you will come into the centre, everything above and below you will kind of merge to the centre, just at your eye line, okay? So if you're in a long corridor, and that corridor was about, say, half a mile long and straight, and the light on the ceiling, well, the light that's the furthest away from you, half a mile away, yeah, was the only light on, well, you'd be in a dark corridor, right? Right? Yes. Okay, you'd be in a dark corridor. So as you start walking, eventually you'll see a little light on the horizon. It gets a little lighter. And as you get closer, that light will rise until it's overhead, and if you carry on walking, it will set again. Yeah? So the sun doesn't literally rise and set. It literally gets closer to you and then further away. That's all that's happening.
There was a famous experiment conducted by Eratosthenes. Eratosthenes. And there are two cities in the old world, and one of them, they knew that at 12 noon on a particular day of the year, that the sun was directly overhead and you could see the bottom of a well.
Oh, okay.
You don't run around looking at the bottoms of wells.
No.
Because the light doesn't take, it's just, no.
Doesn't get down there.
Doesn't get down there.
How can we use this observation to see if Earth's surface is curved? We needed another well. Turns out we can't see the bottom of both wells at the same time. What might explain this? Well, there are two possible explanations. First, we could have a flat Earth with the sun that's small and close by, so that the light hits the second well at an angle. Or second, we could have a curved Earth with a sun that's big and far away, so that all the light comes in parallel, but only one well at a time is lit all the way to the bottom. Turns out with just two wells, there's enough wiggle room for both explanations to fit our observations. Eratosthenes only had two wells, but what if he had added a third? With a third well, it doesn't matter where the sun is. No flat Earth model can explain the angles of all three shadows. But the spherical model explains it all. all three angles with ease.
Right, that was interesting. That was our friend Neil again, explaining Aristotle's, I call him Eratosthenes, I don't know how he pronounced his name, but that experiment was again a supposed proof of the globe Earth. Right, so these are the two graphics that he showed. He was actually very quick on showing one of them, and there's a reason why. Because if you, I don't know, it's not coming out very well, but if you project down from the sensor well, what now?
It's a touch screen.
Oh, touch screen. No, you didn't tell me that. Yeah, so if you project down from the sensor well, and then project down from that well, yeah, you get the centre of the Earth, right?
Yeah.
Right. What happens then if you project from this one? This one doesn't match. Yeah? So that was a bit of deception there to show that, you know, if this was real, he wouldn't need to do this kind of deception. So another thing he mentioned was that in order for this model, Eratosthenes' calculation to be correct, all the light from the sun has to be parallel. Okay? He said that in his little explanation. But that's not what we see. On a day when there's broken cloud, yeah, the light comes down at angles. Has anyone seen that?
Yeah. Yes.
Yeah, it's our observation. Yeah? This is the thing. In their model, light has to come in parallel for Eratosthenes' calculation to be correct. But when there's an eclipse, now light comes in at all sorts of angles. It's the only way to explain how the moon can cast a smaller shadow than the moon itself. Okay? So, which one is it? Right? It's a contradiction in their model. Because the eclipse doesn't look like this. That's the only way that umbra-penumbra idea can work, is if the sun is like huge and close to the moon, and so it's shining around the moon and creating all these angles. But that's not the case, because apparently the moon is 400 times smaller than the sun, and the sun is 400 times farther away. So they literally cancel each other out and appear exactly the same size in the sky. So no, again, this is a contradiction in their model. So you know, according to Neil deGrasse Tyson, he basically lies about stuff, so you can't really trust him.
Fair enough.
And also, if you caught it, he actually said Eratosthenes did not prove anything because he only had 2 wells. So he literally said that is not proof. So the curvature that you can expect to see is a drop of 8 inches per mile squared. Okay, for a circumference of 25,000 miles, that's a drop you're going to see. Okay, and you can actually do this in AutoCAD, and you know, draw up the Earth in AutoCAD and actually measure it yourself. Okay, so you can go out knowing the distance of things and literally decide how much you should be able to see things. So here's one example: the White Cliffs of Dover from Boulogne. Okay, well, it's 31 miles away, and according to the calculation, right, it should be 353 feet missing. It should be hidden by the curvature. But the highest point of the White Cliffs of Dover is 350 feet. So it should be 3 feet under the curvature. But as you can see from this photograph, you can see virtually the whole of the White Cliffs of Dover. And there's plenty of other examples. Yeah, there's the Isle of Man from 65 miles away, Chicago skyline 53 miles away, and the world record, actually world record amateur long distance landscape photography is, I think it's what, 273 miles. Yeah, looking at 2 peaks in France. So this picture, this is one of those pictures. This is across Lake Michigan, looking at the Chicago skyline. Okay. Now people will say that because you can't see some of that skyline, well, there you go. That's proof of the round Earth. Okay, some of that skyline is missing. They kind of conveniently forget that with that calculation, you should only be able to see the very top of, I think it's this one. Okay, but just to dispel this idea that that hidden portion is because of curvature, is this experiment. Start to disappear. Isn't curved. Okay? Obviously there's a flat field, he's just walking off into the distance and the camera is actually on the ground. Think about here, he turns around. So there you go, he's at the end of the field, and I think he dips down, there you go, disappears behind the curve. Yeah? No, he doesn't. Another thing, another proof is in a plane, there's a thing called the altitude indicator, the artificial horizon. Okay? The artificial horizon is basically based on a gyroscope. Yeah? So in here, there's a gyroscope that's spinning up, and literally it's on gimbals, so that if you move the actual thing around, then the gyroscope will stay in position. Okay? So a gyroscope has a very important quality called rigidity in space. That means when the gyroscope is actually spinning up to speed, yeah, it will stay in its orientation no matter what. Okay? It doesn't matter where it is on Earth. Doesn't matter, you know, whether it's in space or on Earth or, you know, anywhere on Earth, doesn't matter. It will stay in its orientation. So, before a plane takes off, it spins up its gyroscope so that it can get the reference to the flat Earth, the sort of, you know, where the Earth is, okay, at that point. So, there it is. Its gyroscope is upright, so it knows where the horizon is. So if it takes a flight, say 4,000 miles, okay, literally it will go around the curvature of the Earth, but the gyroscope will stay upright as the plane goes over the curve of the Earth, yeah? And that would mean that the artificial horizon should roll backwards during straight and level flight. It doesn't, okay? One of the arguments against this idea is this thing called, and you'll hear it if you look into it, pendulous vanes. It's an idea, it's called a self-erecting mechanism, so that supposedly when the gyroscope starts to move, then these vanes open and let air go out and sort of erect it again. The problem is with this, it wasn't designed to do that. It was designed to stop something called precession. Okay, so if you hear this argument, just actually look into it and you find it's got nothing to do with you know, correcting for the curvature of the Earth. On that subject, if a plane flies straight and level, okay, straight and level flight, it would have to dip its nose down, and literally, if the plane's going at 600 miles an hour, after an hour, it would have to correct for 43 miles of curvature. Planes do not dip their nose down in straight and level flight, right? In fact, there are things called trim tabs, on an aircraft, where the control surfaces of an aircraft determine where that aircraft or what height that aircraft is flying, or what attitude that aircraft has. And what you can do is when you let go of the yoke, right, it should fly straight and level. But sometimes it doesn't, and there are various reasons why it doesn't. And you would set this thing called a trim tab, which is that control there, just to adjust it so it flies straight and level. Which means it will not follow the curvature of the Earth. It will literally just fly straight and level according to the air that's flying over it. Okay? So if you're on a plane over a globe Earth, literally you would start off at a height and fly in a straight line and fly off into space. But that doesn't happen. Right? Planes fly over a plane. That's why they're called planes. So the only proof we have that there's something going on, or something other than what we see going on, is NASA. Can we trust NASA? No. Okay. It's very difficult to see this, but this is the globe here is the blue marble image from 1972. The only shot that NASA claims is an actual photograph of the Earth. Okay. So we've taken a picture from the ISS, which is at 400 kilometers, yeah, about 250 miles up, and we've taken one of their photos with their curvature and mapped it on this globe, and it fits. Okay, even though it's only taken from 400 kilometers away, yeah. Where the Tesla Roadster apparently is in space, what a load of rubbish that is, yeah. Same thing, we've mapped it and it was only 200 kilometres up. So their curvature does not make sense. So as I said, this is the only image that NASA will say is a real photograph. Right? Every other photograph that NASA puts out into the media is a composite, it's Photoshop.
Blue Marble 2.0.
This is a guy
NASA's Rob Simon made this. Simon's job is...
It's primarily taking data and making pictures out of it.
That's what this is. A composite of data sets from several different instruments translated into a picture.
So we actually had to take clouds out.
They stashed the clouds for later and went onto the ocean. That came from an instrument that measures phytoplankton in the sea.
Where it was low, I colored it dark blue because they're low mostly in mid-oceans. And then where it was a little bit higher, it was like a little bit brighter green.
Then add the clouds back in.
There's a small problem with it because there's a very slight gap in between each orbit.
So some of those are painted on.
It is photoshopped, but it has to be.
Then
there was another layer to sort of simulate the atmosphere.
And then there's this little bright spot.
It's called the specular highlight. So it's the reflection of sunlight off of water.
Those are the pieces, but you can't just slap them all together.
It just didn't look realistic. It looks kind of flat, or the clouds are sort of too see-through. So I just hit Command Z a lot.
There's artistry to creating the world.
What I imagine it to be. Unfortunately, I'm not an astronaut. I've never been to space. But I've looked at these images over and over again, trying to sort of get the essence of it. It is photoshopped, but it has to be. It is photoshopped, but it has to be. It is photoshopped, but it has to be. It is photoshopped, but it has to be.
That should be a stunning admission for you, right? All these photographs, so-called photographs of Earth from space, are not photographs. He said it himself. They are images generated from data sets, numbers, yeah? And you've got artists creating images from numbers, okay? Which is why again, you can't see it very well, but all these shots of Earth that they've put out, they're all different because they have different artists making them up. And one of the reasons they say, you can't literally take an actual photograph from space because we don't have satellites far enough away to actually take the photograph. Well, again, it's difficult to see here, and that's a mistake. The scale is 1 pixel is 100 miles. Okay, this is where the 1972 shot was taken from. Yeah, and this is a satellite, supposedly a satellite in geosynchronous orbit. yes, they can take a shot of the whole Earth, you know, according to their model, right? And while we're on the subject of satellites, this is the kind of typical size of a satellite. It's kind of like a size of a large car, or between a large car and a school bus, okay? Now, you can sit in a field at midnight. I'm going to have to start this one. You can sit in a field at midnight and look up at the sky, and every so often, and it's again very difficult to see, but every so often you should be able to see what they call a satellite moving very slowly from horizon to horizon. Has anyone seen one? Yeah? Okay. Consider this. Consider this. This is again a scaled image of the Earth, and this is the orbit the ISS has. So if you can see, that's a literal distance. It's 250 miles. Yeah. Low Earth orbit starts at 99 miles, so even tighter than that. Okay. And this is the limit of low Earth orbit, 1,200 miles away. Now, the sun is over here, and you can just about see that there's like sunlight streaming either side of the Earth. Yeah. So this is Earth's shadow. If you're somewhere around here, it's midnight. It's around about midnight. Okay. And if you see a satellite going past horizon for horizon, how are you seeing that? It's moving in Earth's shadow. Satellites don't have lights on them. The only light, supposedly, is coming from the sun, but these satellites are in Earth's shadow. You won't be able to see them. And then consider this. Even if somehow you could get sunlight to it and see it, do you think you could see a car from 99 miles away? Yes. Let alone 1,200 miles away. Really? Okay. A jet engine on a 747 is about the same size. Okay? When a plane is flying over at 35,000 feet, that's only 7 miles away. Can you see the engine on that jet as it's 35,000 feet? Can you see the jet? Oh, you reckon you can see the actual engine on that jet with the naked eye? No, you can't. Imagine if do you think you can see that at 99 miles away or 1,200 miles away? No, you can't. So this is what we found out. Satellites are being launched from Antarctica, okay, on balloons. Yeah? NASA is the greatest or the biggest user, NASA is the biggest user of helium on this Earth. I wonder what they're using that helium for. And this is a rare occasion where one of their satellites fell to the Earth. Okay? And it's attached to a balloon. So, you know. So you see the balloon there. So, okay, we'll move on to their ideas about the moon. Okay? Here is a picture from, apparently taken from the command module above the moon's surface. The problem is, the Earth there is the size of the moon from the Earth. Okay? So, when we see the moon and it's nice and big in the sky, right, the size of that moon is the same size as that picture. The Earth is 4 times the size of that. It should look like that. They made a mistake there. Here are all the landing sites. Here are all the landing sites of the Apollo spacecraft. Okay? Now bear in mind, this face of the moon is always facing the Earth, right? Okay? Apollo 11 landed here. This is one of the images here of Buzz Aldrin coming down the ladder. The Earth is here, near the horizon. As I said, this face of the Earth, of the moon is facing the Earth. How could it ever be on the horizon? If we go back to this image, Apollo 11 is only, as I say, 15 degrees off overhead. Yeah? So right here, the Earth is directly overhead. You know, here it's about 15 degrees. The Earth there isn't 15 degrees off overhead. Yeah? Same here in this inset. It's a bit higher, but it's still not anywhere near overhead. The other thing is that the moon is bright enough to light up the whole side of a planet, okay? Enough so you can see to do stuff from 238,000 miles away. Imagine how bright it must be being up on that moon. It wouldn't be this grey surface. If it's got the power to light up the Earth like that, it would not be that grey surface.
I'd go to the moon in a nanosecond. The problem is we don't have the technology to do that anymore. We used to, but we destroyed that technology, and it's a painful process to build it back again.
Right, that was a stunning admission by Don Pettit, saying that we cannot go to the moon again because they've lost the technology. Does that make sense to anybody? No. Okay. This is a guidance computer on the Apollo 11. Yeah. It had something like what was it? 64K of memory. Yeah, an 8-bit processor, and I think it's a 43 kilohertz CPU. Yeah, an iPhone today is like 32,000 times more memory. It's got 32 times the processing power, and 218,000 times quicker than that. And somehow they can't go back to the moon. You know, the space shuttle, if they repurpose the space shuttles, go to the moon, right? It literally can match the performance of the Saturn V. They can't get there, doesn't make sense. And if we can't go to the moon, how come they managed to send 4 robots, supposedly, to Mars? Does that make sense to anybody? No. So perhaps we can't make a lunar lander. I invite anybody to get close-up shots of the lunar lander on the moon. And you can you see that? It's made up of curtain rods, gold foil, and construction paper. It's rubbish. Yeah, it was designed to fool people back in the 1960s. Yeah, now we can have a look at it with our computers. It just doesn't make sense anymore. So you know, it's just so ridiculous. Does not even deserve our attention. And that's it in a nutshell.